Okay, so we're talking about nonlinear system, and the goal here in this chapter is not to find the full solution of the nonlinear system yet, but we want to anticipate, by using our knowledge of linear system, we want to anticipate how the behavior of the nonlinear system will be. For that, we need to linearize our set of differential equations. So here's the linearization process. And something that I didn't mention, but because we're linearizing the functions around the equilibrium point, when you evaluate each of these functions, f1, the derivative of x1 at the equilibrium point, this will be 0. That's the equilibrium point. The same thing for the second derivative and the last derivative. Because this is the equilibrium point, this term will be 0. By neglecting the higher order terms, then we obtain this linear representation, and we will have this matrix. And if we calculate the eigenvalues of this matrix for all the equilibrium points, we can have an idea of how the system will behave. So that's what we did, and we worked with the system that we worked before. We have 3 equilibrium points. We linearize the system. Basically, we get the matrix A around each of the equilibrium points. So the matrix A, which is going to be the derivative of the function f1 with respect to x1, derivative of f1 with respect to x2, and here, derivative of f2 with respect to x1 and x2. By getting those derivatives, then we get this generic matrix. By evaluating this term now at the equilibrium point, in this case, x1 is 0, so we evaluate that, we obtain the matrix, get the eigenvalue, and we got the first conclusion. The first point, 1, equilibrium point, is a stable focus. Stable because the real part is negative, and it's a focus because you have an imaginary part that is different than 0. Point 2, we proceed in the same fashion. We have the matrix already. We just replace the value of 2. So x1 at the equilibrium point now is 2. We replace that. We got this matrix. We got the eigenvalues, and this is a saddle node, unstable. The system is unstable in that point. And finally, the last point is x1 negative 2. We replace that there. We got the same matrix. Got the eigenvalues, which are the same. This is a saddle node. So to verify this, then because we're not going to get the solution in this chapter, we're going to work on that in the next chapter 4. But for now, we can use Wolfram alpha, and we can get the string plot. And you can use this command and put the equation in the range in which you want to plot the variable x1 and x2, and then we can get the phase portrait. This is the solution of the system. The trajectories in the phase plane starting from different equilibrium points, different initial points. So that's what we got, and effectively we got a good description here. This is a stable focus, and these 2 equilibrium points, as you can see them there, are saddle nodes. So we will continue with that today. Is there any questions so far? No? Yes.
So you mentioned the mathematical characteristics of a nonlinear system, like how there's multiple equilibrium points and stuff. But as far as like the physical characteristics, I know in the power flow problem, we model the load as a power. So that's dependent on the voltage. So that makes it nonlinear. But what other physical characteristics in the power system make it nonlinear? Or because it's nonlinear, what are some physical characteristics?
Yeah, I mentioned last class that the nonlinearity can come from the generators, or it can come from the load itself. As you said, if we assume that the load is constant power, yeah, that will create that the power flow equation are going to be quadratic in form. But if you assume another characteristic, then the load might behave in a nonlinear fashion as well. Different fashion, not quadratic, different fashion. Then you will have some nonlinearities there. Also some dynamic behavior, not of the machine, maybe from some components that control the machine, they might be nonlinear. So you have a governor, for example, that might have some nonlinearity there. and that will add some to the complexity of the model. But we will get there. And as I said before, we're going to review the pendulum. Why? Because in the most simple way, we can see some resemblance of this pendulum with the synchronous generator. So we will see how this works. So the pendulum, what is the assumption we have here? That you have a rod here that doesn't have any mass, weightless, has a length L, it's rigid, and this ball will have a mass M. This is going to be the pivot, and then you can add some initial speed to this ball, and then the ball might follow a trajectory somewhere along this circle, the circle of radius L. Yeah. So how we can come up with a representation of this? What we're going to do in this case, we're going to see the behavior along the tangent. So this ball will have a movement along the circle, but we're going to formulate the equation exactly at the tangent of this circle. So what we're going to see there, first of all, we need to define some variable. And the variable we will pick is the angle theta. So this vertical line is going to be a reference to measure that angle theta. When theta is 0, it's because the ball is here at the bottom of the circle. So if theta is positive, the ball will move in that direction. If theta is negative, the ball will be somewhere here. And this is going to be periodic. So if this is theta, the position of the ball will be there, but it will be the same position if theta is theta plus 2 pi. It means that the whole position, everything will be repeated with a period of 2 pi. So to get the motion along the tangent, we're going to get the arc of this trajectory using the variable theta. So we know that the arc, the distance here along the circle of radius L, this distance is going to be theta times L. So all this distance here will be theta times L. You have the arc S. Now we can get for the S, we can see how that S is changing in time. If you get the derivative of this in time, you will get the speed along the tangent. So the speed along the tangent will be, we replace S here, and as L is constant, get out of the derivative, and the speed is going to be L times the change in the angle theta. We can get the derivative of the speed, and then because L is constant, we derive this one more time. It's going to be L, the second derivative of theta in time, which is the angular acceleration. So that's what we're going to consider. We're going to consider the motion at the tangent here. So by applying Newton's law, we observe what are the forces that we have in this ball. And the only force that we have in this case is going to be mg, the force due to gravity. So the gravity will try to push the ball in a direction, in a negative direction with respect to theta. So we'll try to bring the ball back to this point. So the forces, all the forces that are applied, because the equation we're getting are described along the tangent of this trajectory. We can get the composition of this force along that tangent, and we can observe here that the angle you have here is the same angle theta. So if this is the force mg, then mg sine of theta will give you this projection, which is the force that will be applied along the tangent. And this force is in opposition to the movement. So you will have negative mg sine of theta, and that must be equal to the mass multiply by the acceleration A. By replacing here the acceleration A, we got here, we replace it right there. We can see that the mass get canceled in this equation. And then we can isolate for the second derivative of theta, and you get this second order equation. Yeah? So basically in this equation, because we have not added anything else, what do you think, by looking at this equation, will be the dynamic behavior of this pendulum? We just have the second term, the second derivative of theta in time, plus a term that is going to be proportional to sine of theta, and that is equal to 0. So what do you think? How theta will change in time just by looking at this equation? Will oscillate? In which fashion? So the first derivative of theta and the second derivative of theta is going to be sinusoidal. So how is the behavior? Oscillation without any damping, right? So if I start the ball here and I let it go, what we expect that the ball will start moving forever between these 2 points, yeah, and will oscillate, right? Because we're not adding anything else. We can add some friction, and then this movement, will start like decaying in time because of the friction until we reach that point. That's what we expect. But at this point, we don't have any friction. So this is the equation. Now, how we can connect this with what we obtained before? We're going to define state variable. Because this is a second order equation, we need to have 2 state variables. So the first state variable is going to be theta, the position, and the second state variable is going to be the first derivative of theta. So we pick this state variable, and then we convert that second order equation into 2 first order equations in this fashion. So if x1 is theta, the derivative of this, x1 is the derivative of theta, but that corresponds to x2. So that's the first equation. Then we get the derivative of x2, which is the second derivative of theta, and we get that equation from the second order equation, which is this one. So in vector form, this is the state space representation. As you can see here, this is a nonlinear model because the second function f2 is actually nonlinear, sine of x1. Now that we have this representation, then we apply what we discussed so far. The first thing is to find the equilibrium point for the system. So we get the derivative of each of the state variables to 0. The first one is easy. x1 equal to 0 means that x2 is equal to 0. So what is x2 in this pendulum? Is the speed. So at the equilibrium point, the speed needs to be 0. So that makes sense. Then we have x2 dot equal to 0. And then we need to solve for x1. And because this is a sinusoidal function, what values of x1 will lead to an expression here that is equal to 0? Infinite. So if x1 is 0, pi, 2 pi, 3 pi, and so on, and also negative, all those points are going to be equilibrium points. So this system will have infinite equilibrium points. And here we have a solution for that. So for any integer here, that's the equilibrium point for x1. x2 is always 0. So because this function is periodic, we can just pick the 2 equilibrium point between 0 and 2 pi. And that's what we have. So we will pick 0, and then we will pick pi. 2 pi will be exactly the same as 0, and this will be repeated. So we have 2 equilibrium points that we will study, and we want to realize what is the behavior actually in these two equilibrium points. So we linearize the system, that's the next step. We have the function, so we need to get the derivative of this with respect to x1, that's 0. Derivative with respect to x2 is 1. So we will have in the first row of this matrix 0 and 1. Second equation. Derivative of this with respect to x2, that's the second term of the second row, is going to be 0. But the first derivative is going to be negative g over L cosine of x1 at the equilibrium point. So that's going to be our matrix. Now that we have linearized the system, we study the behavior around each of the equilibrium points. So we take the first equilibrium point, 0, 0. We evaluate the matrix when x1 is 0. And then this cosine of 0 is 1. So you have 0, 1, negative g over L, and 0. So we get the eigenvalues of this. And we get this equation. So we get the square root of negative GL, and that is a purely imaginary number. So what is the solution for point 1? How is the behavior of the system around point 1? It's going to be a center. Yeah. So any point that we have that is follow this pattern is 0, 2 pi, 4 pi, and also negative. All of them are going to be a center. The next point is going to be pi and 0. So we apply the same thing, but now cosine of pi is going to be negative 1. And because this is negative 1, with a negative, then this becomes plus g over L. So we have this here. And again, we get the characteristic equation. We solve, and in this case, the solution for lambdas are going to be two real quantities. One is positive and the other is negative. So we conclude that the points in this sequence, all the points in this sequence are going to be saddle node points. So in the pendulum, what do we have? What is 0, 0, or 2 pi, or negative 2 pi is when the pendulum is at the bottom. Do we expect that that is going to be a center? Yes. You start without any friction. The pendulum will move forever between 2 points, right? If you start at the top of the pendulum, in this circle, you put the pendulum, the mass at the top, what do you expect? Somehow we can balance this should be there, but that will be impossible. This is a saddle node. So any tiny deviation from that point will make the trajectory to deviate from that. So this is going to be an unstable point. So if we get the phase portrait, we use Wolfram alpha. We have the state space model. We put it in the stream plot. This is what we get. So this is exactly what we obtained before. So if you are at 0, x1, and 0, x2, you have a center. But if you go at 2 pi or negative 2 pi, then you will have a center too. And any other multiple of those points, every 2 pi, you move to the right or the left, these are going to be centers. If you look at what happened at pi or negative pi, then in any other points that are 2 pi away from this to the positive side and negative side, these are going to be saddle node points. So that's the trajectory. So you can see here, if you start the pendulum somewhere here in this trajectory, you will see that the system will be trapped there and oscillate forever. If you have an initial speed, for example, in this case, the position of the pendulum is back here. If this is 0, here, the point here for theta is negative 6.9. By the initial speed of this is going to be 15 radians per second. So you start the pendulum, what is 6.9, negative 6.9? How much is 2 pi? 6.2 and something, right? So this is maybe a few degrees negative, right? And you start from there, the pendulum is there, and then you push it with an initial speed, 15 radians per second, you push the pendulum. So the pendulum, what the pendulum will do, will follow this trajectory. Who can help me to describe this trajectory here? What is going on? Yeah, forever?
Yep. Loss, damping.
When you are at the bottom or the top of the pendulum in this red trajectory. So here you have position. So the position will keep increasing forever. And the speed will change from this minimum value to this maximum value. The top is at the top, the speed is going to be the lowest, and at the bottom, the speed is going to be the max. Perfect. Now, what would happen if we add friction? So what is the difference in our model? Well, the difference is going to be this friction force, which is going to be negative. It's always in opposition to the movement. And this is going to be proportional to the speed. We will assume some constant here, but this will be in opposition to the movement, as you can see that by the sign. So we repeat the same process here, but as you can see already in this equation, the main difference here in the equation is that we have a first derivative, a new term that is proportional to the first derivative of theta in time. So that's the addition. The second order equation then will have this new term. So this is going to be related to damping. We apply again the state space representation, and this is the model that we get. Once again, the model is nonlinear because of this term. When this is 0, the speed is 0. That's one condition for the to have an equilibrium point. But if this is 0, this term will be 0 as well. So the equilibrium point do not change by adding this friction. Exactly the same equilibrium point as before. So we repeat the analysis now, but the model is different. Now, when we do the linearization, the first row of our matrix A will be the same, but the second row will be different. Now, the second term of the second row will be negative K over M. That's the new term where we are adding. So when this is 0, then we evaluate the matrix. This is the generic matrix. This is the new term that show up because of the damping. And then this is the matrix. We get the eigenvalues using the characteristic equation. And this is the solution we get. So this damping typically is a small coefficient, small coefficient. So if this is going to be a small coefficient, this term, what we're going to expect most of the time, that this term is going to be way much smaller than G over L. So this term will be negative, and therefore the eigenvalues will be complex. Because this is going to be imaginary, then the real part here, you see that it's going to be negative, so this is a stable focus. Now, instead of having a center here, because you have damping, the pendulum eventually will converge to the equilibrium point 0, 0, and that is a stable focus. What happened with the other point? Again, we have the matrix evaluated at this equilibrium point where x1 is pi. This is what we get. We solve the characteristic equation and we get the eigenvalues, and this is what we get. as you can see here, both terms are going to be positive, right? So in the extreme, if we don't have this term, how much do you have here? You're going to have k over 2m, right? So when you have the negative term, you will have k over m, because you will have 2 times that term. But when you have the positive, this is going to be 0, right? But if you add the term, then whatever result you get is going to be larger than this. So when you add this second term that is larger than this, it's going to be positive. So that is the general case. One eigenvalue will be real positive, but the other is going to be real negative, and that is still a subtle node point. Doesn't change. The value of the eigenvalue change, but the behavior is exactly the same. So if we use Wolfram alpha again, this is the behavior that we have. The same initial point we take here in red. We start with the pendulum with a small negative angle. We push it. We have an initial speed of 15 radians per second. And the pendulum will go and take one whole loop here, but then we'll start converging to the equilibrium point, which is the stable focus. I have put in Canvas this code, and we can play with the pendulum. Just let me show you this. You just run it, and when my computer is ready, we can talk about it. Come on. There it is. So that's the pendulum. Here I'm going to animate what happened with the pendulum. That's the angle, the initial angle. This is negative 6.9 radians. It's a little negative angle. We start from there. And the initial speed is going to be 15 radians per second. So we'll have an initial speed. So this will move in that direction. So this is the animation of the pendulum. Here we're going to have theta and the derivative of theta in time. So how that will behave. And here we have the phase plane. We have theta and the derivative of theta. So if we're going to be in a stable focus, then we should observe the spiral here converging to the equilibrium. So I have put this pause here so we understand what is the initial point, and now we can let it run. There, and here we go. There it is. So we started with that. We have one whole loop here, and then the pendulum start like going down and moving around the equilibrium point until the pendulum is stabilized and we reach the equilibrium point, which in this case is going to be a stable focus. What can we do with this? Well, you have the code. I want you to play with this. So how you can play? You can play with the mass. You can play with the length of the rod. You can play with the initial condition and see what would happen with the pendulum. So, yes?
In like reality, what would be a situation where the equilibrium point wouldn't be at 0? Because gravity would always bring it to stop that.
But by reference, because this is a periodic trajectory, the pendulum might go and take a whole loop of the circle and still not stabilize. So maybe the pendulum will go again and take another whole loop and continue in that fashion. And maybe after 3, 4 times, finally will be trapped by the stable focus and be stable. But will all that depend on the type of pendulum you have? What is the mass? What is the leg? And what are the initial conditions? So that's why you have the code. What I want you to do is to play with that. So let's see what we get here if we change it. So the function here that I created, That is the solution. We will study in chapter 4 how to get the solution. Then you have a part that is related to the animation, but at the very end of the code, here you have the model. This is the model. So the data is here. Where is the data? It's data there. The data is down here. There. So one thing we can do, we can play with this. Instead of having a damping coefficient of 0.08, we make it a little bit smaller. And we will see what happens. And then I want you to play with the mass and the length of the rod. So that's the same initial point, and this will be the behavior of the pendulum. 1, 2, 3, and 4. Finally, it got stopped, and now the trajectory is being trapped by the stable focus, and the pendulum will be stable. Yeah. So it has to, it took like almost 4 seconds to finally for the pendulum to stop and being trapped by that stable focus, and the pendulum will be stabilized eventually at this point. What is the difference with what we had before? What can you tell?
Takes a lot more time to.
Yeah. Takes a lot of
Yeah, a lot more
time to converge to the equilibrium point. Take a long time to reach this area. We call this the region of attraction. The system gets close to the stable focus and is being trapped by that, and the trajectory is attracted to that point and finally will converge to the equilibrium point. So when we are in the region of attraction, also this will take longer to stabilize. So at the beginning of this course, I show you this animation from the frequency measurement in the Eastern interconnection. There was a failure in one part in the south, in Florida, and that created a release of energy. That energy was sent back to the system, and the machine in the northwest, also northeast, received that energy, started speeding up, while the machine in the south slowed down. But then that energy later came back to the south, and the system started with some oscillation. The oscillation died very quickly. I don't remember exactly. I think a matter of 3, 4 seconds, maybe 5 seconds. But this is what we are observing. You know, the system might go into a long oscillation, and that can be dangerous. In this case of the pendulum, yeah, we need to add more friction to the pendulum somehow. So when we have this design, we need to add some friction there that can stop that movement. Wow. In the power system, what we're going to do? We need to add that friction. We need to add that damping into the system. But what we're going to do exactly? We're going to get there. But this is an initial, visualization of what a physical component, how a physical component might oscillate. So the code is there. I'm going to leave that for you to play with. We talk about another system, and that is the other system, a double pendulum. And I said that a double pendulum is an example of a system that can be chaotic. So here you have 2 rods, weightless, different dimension, and you have 2 balls with different masses, or equal masses in this case. I'm not sure. I need to check the data. We started both of them from an angle pi over 2. And this is how the double pendulum is behaving. Look at the phase plane and look at the trajectory. So that's something that is really hard to predict, anticipate. And look at the animation here and how this a double pendulum is moving in time, and sometimes you see behaviors and movement that are very hard to anticipate, like that one. And you can keep playing with this, and you see that these behaviors are not repeated. You don't see any periodic behavior like in the single pendulum. You might not even have the same behavior when you're moving up here. So far, it's very similar, but you can tell that they're not exactly the same. I think at some point here, around 8 seconds or 10 seconds, you will start seeing very crazy behavior. Yeah. But I put that in Canvas as well, so you can play with that code and see what is a double pendulum. I will pause this and quit it. All right. Any questions so far? To summarize what we did in this chapter, basically, we are understanding the behavior of nonlinear system. This is our first approach in how we're getting our understanding by getting the equilibrium point of the system and getting a linearization of the model around the equilibrium points. So we can anticipate how the system will behave around those equilibrium points. So that will give us a first picture of how the system will behave. Yeah. So to finalize this chapter, I want you to work on the problem 3.1 and 3.2 from the notes, but with you, we're going to work on these problems. Yeah. So that's the first differential equation. And the second is this one. Yeah. So what we need to do here is to sketch the first phase portrait of the system. So you have a nonlinear system, yes, because the derivative of the state variables are nonlinear function. Yeah. So what is the first thing we need to do here?
Find the equilibrium.
Find the equilibrium point. Step 1, equilibrium point. So we will get the derivative of x1 with respect to time and make that equal to 0. And that is equal to x2. I can factorize here by x2. And we get this. So if this is equal to 0, here we have two choices. So this implies that x2 can be 0. That's one choice. But the other is that this x2 squared is 1. Because this is square, then x2 can be plus 1 and negative 1. So x2 can have those three values. If we look at the second derivative here, and this is going to be equal to 0, then we conclude that x1 needs to be equal to the negative of x2 squared. So for each of the value of x2, we can determine the value of x1. So from here, equilibrium point point 1 is going to be x1. When x2 is 0, then x1 is going to be 0. That's the first equilibrium point. Second point, then x2 is going to be plus 1. Then x1 is going to be negative 1. And final point 3, x2 will be -1, but again, x1 will be -1 as well. So in the phase plane, we're here. Then we will have -1 for x1 here. This is going to be x2. Here we will have 1 for x2. So you have a point here, and then you will have a point right there. So we have 3 equilibrium points. So what we need to do now, the second step, is to study what is going to be the behavior of the system when we're close to those 3 equilibrium points. So before doing that, I think it's better to put here as a step 2, we need to obtain the linearized system. So basically, we're going to deal with a linearized model. And this is going to be the derivative with respect to x1 is going to be 0. And the derivative with respect to x2 is going to be 1 minus 3 x2 squared. The derivative with respect to x1 is -1, and with respect to x2 is -2x2. All this matrix is going to be evaluated when x is equal to the equilibrium point. And all of these will be multiplied by delta x, delta x1, and delta x2. So that's the linearized model. Now, the step 3 will be to analyze the system behavior in each one of those equilibrium points. There. There. Step 3 So point 1, so x1 is 0 and x2 is 0. So the matrix of the system, when we have those points, will be, the first row is going to be 0, 1, and the second row will be -1, 0. 0, 1, -1, and 0. So what we need to do here is to obtain the eigenvalues for this. You know? So what is the eigenvalues for this matrix? Can you tell me just by looking at that matrix?
Wait, no.
No.
-1.
So we get the characteristic equation here. So it's going to be lambda, -1, 1, and lambda. So the determinant of this is going to be lambda squared plus 1 equal to 0. So lambda will be the square root of plus minus the square root of -1, that is plus minus j. What kind of behavior do we have then for that equilibrium point? It's going to be a center. If we get very close to that point, it will behave like a center. Point 2. So point 2 will be x1 is -1, and x2 will be 1. The matrix in that case, x1 is 1. So we get here, if this is 1, you have -2. You have 0 and -2. And on the bottom, you have -1 and -2. That's a matrix. And we repeat the process. We get the characteristic equation here. So we get lambda 2, 1, lambda plus 2. And we get the determinant of this, which is this one. We get the quadratic term, we get the linear term, and the constant term equal to 0. So the solution here for lambda will be negative b, which is 2 in this case, plus minus b squared, which is 4, negative 4 times a, which is 1, and c, which is -2. Negative with negative become positive. All of these is divided by 2 times a, which is 1. So here we can factorize by 4. We can factorize by 4. And the square root of 4 is 2. So that 2 will get canceled with this one. So we will have -1 here, plus minus. And the other term, when we factorize by 4, is 1 plus 2, that is 3. So that's the square root of 3 is 1.73 and something else. When this is negative, you will have a real negative quantity. But when this is positive, you have a real positive quantity. So this is going to be a saddle node. So we obtain a saddle node. What else should we do with this? What else would we discuss when we have real eigenvalues? We gave a meaning of the eigenvector. The eigenvector will split the space and define regions in which the system will behave. If you start in one region, you don't leave that region, at least close enough to that equilibrium point. So what we're going to do here, we're going to get the eigenvectors to get an idea of how the system will behave around that equilibrium point. So let me do it here. And we get the eigenvector. So the eigenvector we pick for lambda 1, q1. So we have lambda 1i minus a multiplied by q1. So we have this situation here, and we will pick lambda 1. Let's say lambda 1 is -1 plus the square root of 3. That's lambda 1. So if we replace that here, we get lambda 1. Here you have 1, you have 2, and here you have -1 plus 2, that will give you +1 plus the square root of 3. All of these multiplied by the eigenvector. Because this is real, the eigenvector will be real as well. So let's define that A and B correspond to the eigenvectors. And this need to be equal to 0. Because this is going to be a singular set of equations. One is linearly dependent on the other. How can we show that these are linearly independent from each other? We multiply the second equation by this term, and we add the two of them, right? What we're going to, or no. We multiply the second equation by this term. What we're going to get here? 2, because they're going to be equal. Yeah. So is that going to be 2? -1 plus the square root of 3 multiplied by 1 plus square root of 3. How much is that? Right? Is that right? Yeah, so in this case, because these are going to be singular, we're going to pick the second equation. The second equation say that A, 1 multiplied by A, plus this, B, is equal to 0. So the conclusion is that A is going to be the negative of this. So if we pick B to be equal to 1, then the first term is going to be negative 1, negative the square root of 3. So that's the direction of the eigenvector for that. So if this is 1, how much is going to be this one? This is about 1.73. So it's going to be negative 2.73. So this is the stable one. So if, let's say, if we move 1 unit, because B is 1, we move this unit in the direction of x2, we will move 1, 2, 3. We will move 1.73, more or less, something like this. We will move in the direction of x1. So this is going to define 1.3. Here you have 2.73. You have another point, so we can trace that eigenvector in that direction. Of course, this eigenvector will be a good description when we're very close to the saddle node. And this is going to be the one related to the unstable eigenvalue. So if we get close to this eigenvector, then this will push us away from that saddle node point, right? We need to do the same thing for the other. I'm sorry, I am past 5 minutes. I'm very sorry. We will do the same thing for the other eigenvector, eigenvalue. We get the second eigenvector, and we will plot it right here. I need to change the camera. Give me 1 minute, please. I wish we can have a camera that can follow me. Huh? That would be cool. So for those that are online, I was drawing the eigenvector related to the eigenvalue lambda 1, which is negative 1 plus the square root of 3. This is a positive real eigenvalue. This is the eigenvector we get. So because this is unstable, if we get close to this eigenvector, the system will be pushed away from the saddle node point. What we're going to do next, we're going to get the eigenvector related to the other eigenvalue, which is the stable one. So we should get another vectors draw here somehow. We will continue here this class. Yeah. Thank you, guys.